So, imagine you're cruising down the highway.
Right.
You're doing maybe, 70 miles per hour. The ride is super smooth.
Right.
Your electric motors are just humming perfectly, and everything feels completely under your control.
Yeah, that's the ideal scenario.
Right, exactly. But then, deep in the silicon brain of your vehicle, a single high-energy neutron.
Oh, boy.
Yeah, a neutron born from, like, a cosmic ray millions of light years away, it actually strikes a microchip.
It's crazy to even think about.
It is, and it hits with just enough energy to flip one microscopic bit of data from a 0 to a 1.
Right. A single bit.
Yeah, and in less than a microsecond, the complex timing of your inverter is completely corrupted, and your car's motor could just violently surge forward. So, welcome to the invisible, terrifying, and just utterly fascinating world of EV microsecond diagnostics.
It really is a genuinely wild scenario to think about when you put it like that, because we spend so much time worrying about physical hazards on the road.
Right, like potholes.
Yeah, potholes, other drivers, black ice, But when you look at the sheer amount of raw electrical power being managed in a modern hybrid or EV, the margin for catastrophic error isn't measured in seconds.
No.
Or even milliseconds. I mean, we are operating strictly in the domain of microseconds.
Which is exactly what we are getting into today. We are peeling back the layers on one of the most highly specialized, really dense areas of automotive engineering.
Oh, yeah, it's incredibly dense.
We're looking at these technical specifications for hybrid dual motor power control systems, or PCS.
Right.
And we're zooming all the way in on one extremely critical safety domain, which is known as phase voltage and PWM control loss.
It really is the ultimate diagnostic deep end.
Yeah.
Because if the pulse width modulation, the PWM, if that loses control, the electric motor instantly loses its electromagnetic balance.
And when we say, loses balance, we aren't talking about like a slight vibration in the steering wheel.
Oh, no, not at all.
We are talking about severe unintended acceleration, or just the complete physical destruction of the drivetrain while you're at highway speeds.
Exactly.
So we're looking at how engineers achieve what they call ASIL D safety.
Right, the highest automotive safety integrity level.
Right. It's about designing a system that can detect a failure, diagnose it, and physically save the vehicle before the human driver even registers that a single electron went out of bounds.
Because honestly, by the time a human brain processes that something is wrong, the physical damage is already done.
Wow, yeah.
The vehicle's digital immune system, it has to act entirely on its own.
But to really appreciate how incredible that safety net is, we first have to understand the exact mechanisms of how this system fails in the first place.
Right. How do you break an unbreakable motor?
Exactly. So looking at the root cause analysis in these specs, there are 4 distinct physical dimensions to this failure. And the first one takes us right down into the digital timing logic. It's called the GTM timer glitch and clock asynchrony.
Right. So to generate a smooth, 3-phase sine wave of electricity to actually drive the motor, the main microcontroller rapidly switches the high voltage power on and off.
And this uses specific modules, right?
Right.
Like the AUREX, ATOM, or TOM modules.
Exactly, yeah. That switching is the PWM signal.
Yeah.
But to coordinate that switching perfectly, the microcontroller relies on a highly precise reference clock.
And if there's severe electromagnetic interference, that internal clock can actually slide out of phase.
It can, yeah.
And the system enters this state called Mnemonic stability. Now, I got to say, from a digital logic standpoint, Mnemonic stability is just fascinating.
Yeah, it's a huge problem.
Because a signal is supposed to be cleanly a 0 or a 1. But what exactly is happening, like physically inside the chip when it goes Mnemonic stable?
Well, it comes down to the physical transistors inside the digital flip-flops of the microchip.
Okay.
So a flip-flop requires a very specific setup and hold time to lock in a 0 or a 1. But if the clock edge hits at the exact picosecond that the data line is transitioning, because, interference caused that clock to slide out of phase,
Yeah.
internal transistors literally get stuck in the middle.
They just get sent duck.
Yeah, they balance precariously at this midpoint voltage. The circuit doesn't know if it's a 1 or a 0.
Oh, wow.
So it oscillates unpredictably until just random thermal noise pushes it to one side or the other.
Which means the duty cycle values fail to update correctly.
Exactly.
The way I was visualizing this when reading the sources is like a world-class orchestra.
Okay, I like that.
So the PWM signal is the conductor's baton, right? It's setting this flawless high-frequency tempo.
Right.
But if the conductor suddenly loses the beat, that's our clock asynchrony, Then the violins come in a fraction of a second early, the brass is late, and the beautiful music, which is our smooth three-phase sine wave,
Yeah.
it just instantly devolves into chaotic, destructive noise.
That is exactly what happens. In the electrical world, that chaotic noise manifests as corrupted pulse widths.
Right.
You get pulses that are far too narrow, or you get these wide, straight-through pulses.
And that destroys the symmetry?
It completely destroys the voltage symmetry across the motor phases. It creates massive magnetic distortion.
Okay, so that asked the digital clock glitching. But moving from the silicon brain down to the physical power stage, we hit the second major root cause.
Which is the switching delay drift and gate charge loss.
Right, now we're dealing with the actual physical switches.
Yeah, usually silicon carbide or SiC transistors.
And these things have their own hidden physical quirks, right? Like parasitic capacitance.
Oh yeah, parasitic capacitance is basically the bane of power electronics engineers.
Really?
Yeah, because even though it's not a physical capacitor that you soldered onto the board.
Right, it's just inherent to the component.
Exactly. The physical structure of the silicon carbide transistor itself naturally acts like a tiny bucket that stores unintended electrical energy.
And the problem is, the size of that bucket changes depending on the temperature.
It does, yeah.
Like, as the inverter bakes in the engine bay at 120 degrees Celsius, or, I don't know, freezes in sub-zero winter temperatures, the physical properties of the semiconductor actually shift.
Precisely. The threshold voltage changes and the internal resistance shifts.
So the math gets thrown off.
Yeah, the calculated delay between the microcontroller sending the turn-on command and the transistor actually conducting that massive high-voltage current, it starts to physically drift.
But, you know, temperature drift is just one part of this. The engineering specs point to something way more mechanical causing this delay.
Fretting wear.
Yes, fretting wear on the low-voltage connector pins. I have to admit, when I first read this, it really threw me.
Why is that?
Well, we are talking about the absolute highest levels of digital microsecond timing, and the culprit is, like, tiny metal pins rubbing together.
It sounds low-tech, right?
Yeah. How does physical scraping cause a microsecond timing error?
Well, it is the perfect intersection of mechanical reality and digital theory.
Okay, lay it on me.
So in an automotive environment, the entire chassis is constantly vibrating. The road, the tires, the suspension.
Right, it's a harsh environment.
Yeah, it all transmits these high-frequency micro-vibrations straight into the inverter casing.
Okay.
And over thousands of miles, these vibrations cause the tiny metal pins in the control connectors to rub against their sockets on a microscopic level.
And that rubbing wears away the protective chemical coating on the pins.
Exactly. And once the base metal is exposed to oxygen, it oxidizes.
It rusts.
Essentially, yeah. It develops a microscopic layer of insulating rust.
Which instantly spikes the electrical resistance across that connection.
And here is where it actually impacts the timing.
Okay.
Because to turn on a silicon carbide transistor fast enough, and we are talking nanoseconds here, you need to flood its gate with a massive, sudden rush of electrical current.
Right, that's called the gate charge.
Yeah. But if fretting wear has created a bottleneck of resistance at the connector pin, that current is physically choked off.
So the bucket takes longer to fill, the transistor turns on sluggishly?
Yes, exactly. The physical turn-on event is delayed by just a few microseconds.
But that's enough.
It is more than enough. The resulting waveform gets distorted, and suddenly the microcontroller's math just doesn't match the physical reality of the power stage anymore.
Wow.
You start generating massive low-frequency ripples and these destructive electromagnetic harmonics in the motor.
It is just mind-blowing that a microscopic vibration on a single tiny pin can create a literal roadblock for the electrons, throwing the whole drivetrain out of rhythm.
It is wild.
Which actually sets us up perfectly for the third physical vulnerability, high DVDT and ground bounce.
Right, and this is where the sheer speed of silicon carbide becomes a bit of a double-edged sword.
Okay, because DVDT, that refers to the delta voltage over delta time, rate of voltage change, right?
Yes. These set-of switches are operating at staggering speeds. We're talking changing voltage at rates of like 50 volts per nanosecond.
50 volts per nanosecond.
Yeah.
Just conceptualizing that speed is difficult.
It's almost impossible to picture. But when you switch massive amounts of power that violently and that quickly, it acts like an electromagnetic shockwave.
Okay.
It forcibly injects high-frequency common mode noise across all those parasitic elements we just talked about.
Right, the tiny buckets.
Yeah, and that noise slams into the isolation barrier between the high-voltage power board and the low-voltage control board.
And that causes the ground bounce.
Exactly.
You know, I was trying to figure out the best way to visualize the math of a ground bounce.
What did you come up with?
Think of it like trying to accurately measure a child's height against a wall.
Okay.
So the floor is your 0-volt baseline, right?
Right.
If a localized earthquake suddenly lifts the floor up by 2 feet, right at the exact millisecond you take the measurement, you're going to mistakenly record that the kid is 7 feet tall.
Oh, that's good.
Because the measurement relative to the floor is entirely wrong because the floor itself violently shifted.
That is a phenomenal way to picture it.
Thanks.
Because in the control board, a logic low W command might be 0 volts, and a logic high GH might be 5 volts.
Right.
But that high voltage shock wave literally lifts the ground baseline of the control board. The reference point itself spikes up.
So the digital comparator looks at a signal that is supposed to be sitting quietly at 0 volts.
Yeah.
But because the floor bounced up, it falsely reads that elevated baseline as crossing the threshold for an on-in command.
It sees a phantom command.
A phantom command, wow.
And this is terrifying from a control perspective. If the system falsely reads an on-in command due to ground bounce, you can trigger a cross-shoot.
A cross-shoot.
Yeah, where the upper and lower switches of the inverter bridge turn on at the exact same time.
Oh, so you essentially create a direct short circuit right across the high-voltage battery bus.
Yep, completely bypassing the motor entirely.
And the resulting current spike.
It will literally blow the silicon to pieces in microseconds.
Unbelievable. Which brings us to the final root cause, number 4, AFE resistor drift and leakage.
Right, the analog front end.
Now, we've talked about the brain sending commands, but this is about the sensors feeding information back to the brain.
Exactly. Specifically, the phase voltage feedback circuit.
Because the system uses these highly precise resistors to step the massive 800-volt power down to a tiny, readable, low-voltage signal.
Right, so the microcontroller can monitor what's actually happening at the motor phases.
But these resistors are physical components.
They are. And prolonged exposure to extreme thermal cycling can actually alter their crystalline structure slightly.
Which causes their resistance values to drift away from factory calibration.
Yeah, they just become inaccurate over time.
And it gets worse than just heat.
Yeah.
Right? If the physical high-voltage casing fails over time, maybe a seal degrades.
Yeah, that's a big one.
You introduce moisture and road salt into the high-voltage environment.
Which creates the perfect conditions for something called electrochemical migration, or ECM.
ECM, right.
Under high DC voltage bias, moisture and salt cause metal ions from the solder to literally dissolve.
Oh, wow.
And they migrate across the surface of the circuit board, growing tiny microscopic conductive dendrites.
Like tiny metallic tree branches growing between components.
Exactly like that.
That's horrifying.
It is. And when those dendrites bridge a gap, they create a parallel leakage path for the current.
So the resistors are completely bypassed.
Yeah.
So the sensors are now sending wildly corrupted, totally mismatched voltage readings back to the brain.
Right.
The brain thinks the motor is doing one thing, tries to violently correct it by forcing a bad PWM duty cycle.
And the system basically eats itself.
Wow.
It creates the very instability it's trying to prevent because it's operating on bad intelligence.
So we have cosmic-level digital timing glitches, microscopic fretting wear, choking gate charges, violent ground bounces creating phantom commands, and road salt growing metallic trees that corrupt the sensors.
It's a miracle these cars drive down the block, honestly.
It really is. But, knowing how things break is only half the battle.
Sure.
This transitions us perfectly into the safety net, the real-time immune system.
Yeah, because when one of these failures occurs, the clock starts ticking instantly.
Right. And the ultimate deadline for the car to save itself is defined by the FTTI, right? The fault-tolerant time interval.
Exactly. The ASIL D standard dictates the FTTI.
Okay.
From the precise microsecond a fault physically occurs, the entire system has a maximum of 60 milliseconds to detect the failure.
60 milliseconds.
Figure out what went wrong and physically alter the state of the high-voltage drivetrain to achieve a safe state.
60 milliseconds. A human eye blink takes about 300 milliseconds.
Right.
So in 1/5 of a blink, the car has to literally save your life.
And that's just the final deadline. The hardware protection layers actually have to act in under 2 microseconds.
Wow.
It is a highly choreographed, multi-layered defense.
So the first layer is what we can call the software detective, right? The PWM plausibility check.
Right.
The system uses high isolation sigma delta modulators. And these things are wild.
They are incredibly fast.
They are sampling the actual physical voltage at the motor phases and sending a bit stream back to the microcontroller at 10 megahertz.
10 million samples per second.
The sheer volume of data is staggering.
It is. And the software takes that real-time data and constantly runs a high-speed plausibility equation.
Okay.
It compares the expected voltage command at descent against the actual measured voltage coming back from those sigma delta modulators.
It calculates the residual difference.
Right. And the rule is absolutely uncompromising.
What's the rule?
If there is a 10% mismatch between what the car expects and what it measures, and that mismatch persists for more than 2 milliseconds, the software instantly triggers a severe fault protocol.
Because it realizes my commands are no longer dictating reality. We have long control.
Exactly. But as fast as 2 milliseconds is, it is still software time. It requires an interrupt to be generated, lines of code to be processed by the CPU, memory to be accessed.
Right. And what happens if the CPU itself is the thing glitching?
Exactly.
What if the software is a blind? That's where the physical brakes come in.
Yeah.
Hardware dead time monitoring.
Yes.
And we don't need to re-explain what dead time is. I mean, anyone who's touched an inverter knows you absolutely need that microscopic gap between the high side and low side switching.
Right, to avoid that catastrophic cross-shoot we talked about earlier.
Yeah. But what's blowing my mind is how this specific hardware module polices that gap.
It is brilliant engineering because they don't trust the software.
They don't.
No, they built a dedicated physical logic gate hardware module inside the timer unit that does nothing but monitor the physical timing of the pulses.
So if the hardware sees that the dead time drops below 1 microsecond, meaning the signals are getting dangerously close to overlapping due to a clock glitch or ground bounce, or if it detects a pulse that is physically too narrow to be a valid command, it physically blocks the PWM signal from reaching the gate drivers.
It doesn't ask the software for permission.
It just acts.
It doesn't run an algorithm. It just physically cuts the signal path in under 10 microseconds.
It's a literal emergency brake that completely bypasses the digital brain.
And that is critical. In an ASIL D safety environment, you cannot rely solely on software execution time.
No.
You need guaranteed latency. Pure hardware logic gates provide that absolute guarantee.
Okay, so the fault is detected, the cord is cut, the inverter is blocked.
Right.
But you are flying down the highway.
Right, you're still moving.
You have a massive electric motor spinning at 12,000 RPMs. You can't just shut off an electric motor at that speed.
Definitely not.
The kinetic energy has to go somewhere.
Mm-hmm.
The system has to figure out what to do with the car in those remaining milliseconds of the FTTI.
Right. It executes an adaptive response called stepwise ASC, or active short circuit.
Okay.
But it changes its strategy based on the speed of the motor.
So if you are at low speed, say under 2,000 RPM,
Yeah.
the system simply triggers an active open circuit.
Yeah.
It just opens all the switches and lets the motor freewheel.
Exactly. The rotational energy is low enough that it's safe to just let it glide and bleed off naturally.
But if you are at high speeds, and the specs define that as 7,200 RPM or higher,
Right.
opening the circuit is actually the most dangerous thing you could do.
Yes. Because if you just shut the inverter off, the massive permanent magnets spinning inside the rotor act like a giant uncontrolled generator.
It's called back EMF, right? Electromotive force.
Exactly. Because the motor is spinning so fast, it generates a massive tidal wave of high voltage that travels backward into the inverter.
Oh, wow.
It will wildly exceed the voltage rating of the components and obliterate the entire power stage.
Like, think of a massive electric motor at 12,000 RPM, like an incredibly heavy, fast-spinning metal top.
Okay.
If you just grab it suddenly with your bare hand, which is, the electrical equivalent of an instant open circuit. The kinetic energy is so violent, it will snap your wrist.
Ouch.
Yeah, you have to manage the energy dissipation.
And that energy management is the stepwise active short circuit.
Stepwise, right.
Instead of running away from the energy by opening the circuit, the system intentionally leans into it by shorting the motor phases together.
Sorting them together.
But it does it in 2 highly calculated steps to avoid a mechanical shockwave.
So step 1, it triggers a 2-phase short circuit.
Right.
It shorts only 2 of the 3 phases. So using our spinning top analogy, it basically brushes its hand against the side of the spinning top.
Yes. It bleeds off the immediate asymmetrical electrical turbulence.
Okay.
It suppresses the massive transient demagnetization current that would normally damage the magnets.
And it holds that two-phase short for exactly 1.5 milliseconds.
Just long enough for the electrical shockwave to stabilize.
And then step 2, it clamps down with a full three-phase short circuit.
Right, it grabs the top securely with both hands.
This creates a balanced zero-sequence path that effectively caps the DC bus voltage at a completely safe 720 volts.
It is a phenomenal, elegant ballet of destructive energy management. It completely locks down the drivetrain and saves the vehicle in a fraction of a second.
It's amazing. So having a physical hardware kill switch and a stepwise short circuit protocol is an incredible safety net.
Oh, for sure.
But relying on a net means you've already fallen off the tightrope.
That's true.
How do engineers design the system so the fall never happens in the first place?
That takes us out of real-time diagnostics and into the extreme prevention measures.
Right, the DFMEA and PFMEA.
Yeah. Design failure mode and effects analysis, and process failure mode and effects analysis.
Essentially, the philosophy is twofold, right?
Okay.
How do we engineer the blueprint so the physics can't fail? And how do we control the factory floor so human or machine error doesn't introduce a flaw?
Exactly.
Let's start with the blueprint, the DFMEA. And honestly, this first countermeasure is my favorite thing we've discussed today.
I think I know which one you're talking about.
You're telling me I am driving a commuter car to get groceries, and the engineers had to consult astrophysics to make sure my inverter doesn't explode.
Cosmic ray defense.
We are talking about cosmic ray defense.
It sounds absurd, right? Like something out of a satellite engineering manual, not a passenger car.
Totally.
But it is a very real, quantifiable threat to high-density microprocessors.
Because our atmosphere is constantly bombarded by cosmic radiation from deep space.
Right.
And occasionally a high-energy neutron makes it all the way to the surface of the Earth, passes effortlessly through the metal chassis of the car,
Yep.
and physically strikes the microscopic silicon lattice of the microcontroller.
And if that neutron hits a memory register perfectly, it deposits a tiny electrical charge.
Wow.
And if that charge is large enough, it flips a stored 0 into a 1. A single event upset.
A cosmic bit flip.
Exactly.
Which would instantly cause the timer glitch we talked about earlier.
It would.
So to combat rogue star explosions, automotive engineers implement hardware parity checks.
Right. They design redundant logic pathways that constantly calculate and cross-reference their own math.
Okay.
So if a neutron flips a bit, the parity bit no longer matches the data word.
The system instantly realizes the math is physically impossible.
Exactly. It catches the error and flushes the corrupted data before it ever reaches the PWM output.
And they pair that with strict write protections on critical safety registers, right?
Yeah, you have to send a highly specific unlock sequence just to change a value.
Making it, statistically impossible for a random radiation strike to alter the safety parameters.
It is staggering when you think about it.
It is. So that
Right.
solves the cosmic rays. But what about the massive voltage spikes and ground bounds?
For that, the design team mandates the use of laminated bus bars.
No.
They have to keep the parasitic inductance of the entire power stage strictly under 15 nanohenries, with an ideal target of 10 nanohenries.
To put that in context, inductance is essentially electrical inertia, right?
Yes, that's a good way to put it.
When you try to abruptly stop or start massive currents in nanoseconds, that inertia fights back,
Right.
creating those massive voltage spikes, the high dVdt that basically shatter components.
And the physics of how they solve this is just brilliant.
How do they do it?
Well, every wire carrying current creates a magnetic field, right?
Right.
That magnetic field is what causes the inductance. So, to choke off the inductance, engineers take the massive copper plates carrying the positive and negative high voltage,
Yeah.
and they press them incredibly close together, separated only by a paper-thin, high-temperature dielectric layer.
Because the current is flowing in completely opposite directions in those two plates.
Exactly. And because of that, their resulting magnetic fields perfectly oppose each other.
Wow.
By laminating them practically on top of each other, the opposing magnetic fields overlap and effectively cancel each other out.
You essentially erase the electrical inertia through spatial geometry. That's so cool. And just to be safe, they pair that low inductance design with high isolation gate driver chips that are physically rated to withstand transients of 100 kilovolts per microsecond.
Right, you isolate the sensitive brain from the violent power swings of the muscle.
Makes sense. But what about the drift? We talked about resistors and capacitors drifting when the temperature swings, feeding bad data to the safety net.
Well, that's where the DFMEA locks down the bill of materials.
Okay.
You cannot just use standard commercial components. The blueprint mandates Class 1 C0G ceramic capacitors for all critical safety timing and filtering circuits.
So I actually dug into the material science on this because I wanted to know what makes a C0G capacitor so special.
Oh, they're fascinating.
Most standard capacitors, Class 2 ceramics, they use barium titanate.
Right.
And barium titanate is highly sensitive to temperature changes. But more importantly, it exhibits piezoelectricity.
Yes, the piezoelectric effect. It means the physical material actually generates a tiny electrical voltage when it is subjected to mechanical stress or vibration.
Which is insane.
It really is.
In a vibrating car, a standard capacitor might literally create its own electrical noise just by shaking on the road.
It becomes a microphone for road noise.
Yeah. Injecting garbage data into the microchip.
But C0G capacitors use a completely different crystalline structure, typically titanium dioxide.
And titanium dioxide ceramics are rock solid.
They are. They exhibit virtually zero temperature drift from -55 to +125 degrees Celsius.
Wow.
And crucially, they have no piezoelectric effect. You can shake them violently, and they remain electrically silent.
So they pair these completely silent capacitors with high-precision thin film resistors that refuse to alter their resistance values even when baking in the engine bay.
The blueprint is practically flawless. It is radiation-proof, inductance canceled, and thermally locked.
But a perfect blueprint means nothing if the factory builds it wrong. This shifts us to the PFMEA, process failure mode and effects analysis, the manufacturing controls.
Right. Because once the physical board is populated with these perfect components and run through the solder reflow oven, 100% of the critical boards go through 3D automated X-ray inspection, or AXI.
They're using X-ray vision and ultrasonic scanning to look physically inside the solid metal solder joints beneath the chips.
Yes. They are hunting for microscopic voids, basically tiny trapped air bubbles in the solder.
Because an air bubble is an insulator.
Exactly.
If you have a void in a solder joint carrying high current, the heat cannot dissipate into the PCB.
That spot superheats, creating a massive thermal stress.
And over thousands of miles of driving, that joint will physically fracture.
Which leads directly to the fretting wear and gate charge loss we talked about earlier.
So the standard is brutal, right? The total void rate of a component must be strictly under 5%. And no single solder pad can have more than a 1% void rate.
That's right.
But, the detail from the factory floor that I love most is what happens when a board inevitably fails this X-ray test.
Oh, the response is absolute.
Yeah.
It doesn't just put a red flag on a computer screen for an operator to hopefully notice.
No. The manufacturing execution system, the overarching factory software, it automatically triggers physical interlocks on the assembly line track.
It drops a solid metal barrier on the conveyor belt.
The machine throws a literal factory tantrum.
Pretty much.
It outright refuses to let the flawed part move forward to the next assembly station.
It completely removes human error, fatigue, or just oversight from the equation.
That's so smart.
The flawed part is physically trapped on the line until a supervisor uses a highly specific protocol to quarantine it. It is a fantastic integration of digital quality assurance and physical logistics.
And that obsession with precision carries over to the final mechanical assembly, too.
Right.
When they bolt the massive copper power cables to the inverter bus bars, they don't just have a guy with a wrench.
No, they use robotic servo screwdrivers equipped with torque angle monitoring.
And it doesn't just spin the bolt until a torque limit is reached, right?
Because friction from a dirty thread could give a false tight reading.
Ah, right.
So it measures the precise rotational angle of the bolt simultaneously with the torque to guarantee the exact micrometers of clamping force between the metal plates.
And before they even drive the bolt, optical character recognition cameras physically scan the bolts to verify they have the correct chemical phosphate coating.
That coating is vital. Without it, the contact resistance between the heavy cables might creep up.
The spec requires that contact resistance to stay permanently below 5 milliamps.
Yes. Anything higher, and hundreds of amps of current will generate enough heat to cause a thermal runaway fire.
Wow. Finally, before the finished inverter ever leaves the factory, it hits the end of line, or EOL, testing station.
Right.
They don't just assemble it and hope the sensors are accurate. They physically inject a highly precise known AC voltage into the unit.
The system reads the voltage, and the factory computers compare the inverter's reading to the absolute known value.
Okay.
It calculates the exact microscopic error offset of that specific individual circuit board.
And then it burns that specific calibration offset permanently into the inverter's flash memory.
It custom tunes every single digital brain to the slight physical quirks of its specific body.
It is the ultimate manifestation of hardware-software integration.
Absolutely.
So we have a system designed to withstand cosmic rays, built with zero-drift ceramics, X-rayed for invisible air bubbles, clamped by robotics torque angle sensors, and custom calibrated.
The hardware is mathematically perfect.
Mathematically perfect. Now, in the final stage, the engineers try to destroy it.
Yes. This is the production validation phase, the DVP&R, design verification plan and report.
Right.
You can't just assume your math and your manufacturing are perfect. You have to prove it in the physical world through absolute torture.
The first major hurdle is the vibration and thermal shock test. And the parameters are just staggering.
They really are.
They strap the unit to a massive mechanical shaker table for over 500 hours of continuous testing.
500 hours.
They subject it to intense 3-axis random vibration, accelerating the unit at 35 meters per second squared. It is a violent, unending earthquake.
And while it's violently shaking, they put it inside an environmental chamber and rapidly swing the ambient temperature back and forth from negative 40 degrees Celsius to positive 150 degrees Celsius.
All while actively running the system at full operational power, switching those signal transistors at 50 volts per nanosecond.
Right.
The standard to pass this test is uncompromising. The hardware must survive those 500 hours without a single signal interruption lasting longer than 1 microsecond.
If the internal logic drops a signal for 2 microseconds, the entire design fails.
Unbelievable.
And after all that shaking and thermal expansion and contraction, they measure those connector pins we worried about earlier.
The fretting wear.
Yeah. The physical contact resistance cannot increase by more than 1.2 million.
So it physically proves that fretting wear and thermal drift have been completely eradicated by the C0G capacitors and the torque angle manufacturing.
Exactly.
But, enduring a physical beating is one thing. The ultimate validation is the hardware-in-the-loop, or HIL, fault injection test.
Right.
This is where they intentionally sabotage the digital logic to see if the 60 millisecond safety nets actually work.
They take the real physical control unit and connect it to a massive, hyperfast supercomputer that mathematically simulates the physical motor and the vehicle dynamics.
They spool this virtual motor up to 12,000 RPM at absolute full torque load. The virtual vehicle is screaming down the highway.
And then the testing engineers press a button and intentionally inject a 100-per-phase PWM straight-through fault.
Wow.
They manually force a bit flip to simulate the absolute worst-case scenario.
A catastrophic, unrecoverable hardware logic failure.
Yes. The very failure we started this entire journey with.
And the system has exactly 60 milliseconds to catch it and take over.
And according to the validation reports, it executes flawlessly.
The sigma-delta modulators catch the mismatch. The hardware dead-time logic physically blocks the gate drivers in under 10 microseconds.
The system shifts instantly into the stepwise active short circuit.
And the telemetry shows the system safely clamping the massive DC bus voltage under 720 volts, ensuring the inverter capacitors don't detonate.
Right. It suppresses the short circuit current under 550 amps.
And crucially, it proves that the motor's permanent magnets suffer exactly zero demagnetization. They absorb the massive electrical shock wave entirely unharmed.
And perhaps the most amazing metric in the entire report is what this event looks like to the driver.
Yep.
Throughout this entire catastrophic digital failure and high-speed multi-phase short-circuit recovery, the maximum torque ripple, the physical mechanical shudder sent through the drivetrain to the wheels, is restricted to just 5 Newton meters.
5 Newton meters, that's virtually nothing.
It means a driver cruising at 75 miles per hour might feel a tiny, almost imperceptible hesitation in the pedal.
A slight bump.
A slight bump. While underneath them, the car just successfully dismantled a catastrophic microsecond event that, without these specific engineering controls, would have completely destroyed the vehicle.
It is a profound testament to the invisible architecture of safety.
It really is.
I mean, we journeyed from the microscopic threats of deep space radiation flipping bits and the physical reality of fretting wear on vibrating pins.
To the brilliant software plausibility checks and sub-microsecond hardware kill switches.
We saw the sheer physics of canceling magnetic fields with laminated bus bars, the obsession with X-raying solder on the factory floor, and the brutal 500-hour thermal shock gauntlets used to prove it all works.
It really reframes what a car actually is. It's not just a mechanical vehicle anymore.
No.
It is a hardened, fault-tolerant supercomputer on wheels.
Next time you step on the accelerator of a modern hybrid or electric vehicle, just take a single second to appreciate the silent reality beneath you. Millions of calculations, perfectly tuned hardware logic gates, and radiation-hardened silicon are executing flawlessly in the span of microseconds to ensure that your physical intent seamlessly and safely matches the vehicle's reality.
You know, digging through all these validation reports, there is one final, almost throwaway note at the very end of the engineering specs that I think fundamentally points to the future of all this.
Oh, what did you find?
The lead author of the specification offers the broader engineering team a highly advanced Python simulation model.
Okay.
It's a digital physics tool designed to mathematically map what they call the dynamic thermal loss transient coupling of these exact PWM errors.
Meaning what exactly?
It means before they ever physically build a single circuit board or solder a single silicon carbide transistor.
Yeah.
This Python model can calculate the exact sub-microsecond thermal heating boundaries of the silicon based on hypothetical clock deviations.
Wow.
It simulates the physical heat generated by the digital error entirely in code.
Okay, let's just sit with that for a second. We've just spent the last 20 minutes marveling at the intense physical reality of validation, right? X-ray machines scanning for bubbles, massive shaker tables simulating 500 hours of earthquakes, and huge supercomputers injecting physical faults into actual control boards.
Right.
But as these simulation models become this hyper-accurate, calculating exact thermal transients and microscopic physical material interactions purely through mathematics.
We have to ask, are we rapidly approaching an era where physical crash and torture testing becomes entirely obsolete?
Exactly. Will a day soon come when engineers don't need to freeze and shake the physical hardware to prove it works? Will the safety of our families on the highway soon be guaranteed not by physical validation, but entirely by the flawless, predictive mathematical certainty of a digital twin?
It's a fascinating thought.
This is something for you to mull over the next time you get behind the wheel.